VLSos here. This is a video lesson on optimization. We have a problem written here. What is the largest open box that can be made by 5x7 sheet? We're thinking of a sheet of cardboard or a sheet of metal, two-dimensional surface, and we're going to cut it and fold it to make an open top box. This is an optimization problem because I want to find something that is either largest or smallest, an extreme value in the situation. In this case, the largest open box would be the largest volume, the most extreme volume. To get an idea of how to go about a problem like this, it is a very good idea to draw a picture of the situation. We have a sheet of cardboard or metal. We know that its dimensions are 5 inches by 7 inches. And in order to create an open top box, we're going to cut the corners off and fold it. If we cut the corners off the same amount, little squares that have a dimension or side length of x that we have yet to determine, we can fold along these lines into a box that we'll attempt to draw in 3 dimensions. When making a 3-dimensional drawing, you can give the illusion of 3 dimensions, or in this case, an open top, by highlighting or bolding lines that can be seen and softening lines that would be hidden. Hopefully we've created the illusion of a box that has 5 faces because its top is open. The dimensions of this box are going to come from how this was folded. This corner that was cut out is going to become the height. So the height of the box is how I labeled it x. X is the depth of the cut on the sheet. The length of this box is the longest dimension of the sheet after 2 x measures have been reduced because the flaps have been folded up. So this length here is the full 7 inches minus 2 cuts that have been made from each side. Similarly, what we could call maybe the width of the box was 5 minus 2 cuts of x from both sides. I've got the 3 dimensions of my box, and if I wanted to make the maximum volume, then I could start with the volume equation. The volume of this box will be 5 minus 2x times 7 minus 2x times the 3rd dimension, x. What's often difficult in optimization problems is getting an equation for the value or the variable that you're going to optimize in terms of one other variable. In this case, the setup was fairly straightforward. Along the way, we did have the expressions 7 minus 2x and 5 minus 2x that are expressions that we needed to plug into the volume equation, but it wasn't complicated to find the volume in terms of one variable. This here is a function for volume in terms of x. And if we distributed and combined like terms, it would become 4x cubed minus 24x squared plus 35x. If we want to find the maximum volume, we want to do a first derivative test with this. We're going to find extrema when the derivative of an equation is equal to 0. And those extrema could be justified to be maximums, minimums, or inflection points. So we take the derivative of the volume equation. We get 12x squared minus 48x plus 35. which is quadratic. And if we did the algebra, we would get some x values, if this quadratic is set equal to 0, that are not so kind. Plus and minus the square root of 39 plus 12 all over 6. Those zeros are approximately 0.959 and 3.041. These x values are the critical points of the function. They're the places where the derivative of the function is equal to 0, which means that tangent lines are horizontal, and we've reached a maximum, a minimum, or an inflection point. But we still have to justify what kinds of critical points these are by making a sign line for the derivative of the volume equation and highlighting where those critical points are. We need to determine the sign, positive or negative, of every interval in between these zeros. If we put 0 into the derivative, a very convenient value to use that is before the critical point, 0.959, then we will get 0 minus 0 plus 35, which is quite obviously positive. The interval before the first critical point is positive. If we put 1 into the derivative, which is easy to use and directly very close after 0.959, then we get 12 minus 48 plus 35. And the sum of 12 and 35 is 47, so the term negative 48 is slightly bigger, or in magnitude, and therefore the value of the function, the derivative, is negative. We need to find the sign after 3.41. In this case, we could put in the integer 4. Putting that into the derivative gives 192 minus 192 plus 35. These curiously cancel out, and the 35 is left and is positive. So at these critical points, we can now justify that the 1.959 is a maximum because the function is increasing, then reaches its peak here and is decreasing afterwards. We have a max at 0.959, which is what we're looking for. We're looking for the largest volume. And the largest volume will have a cut, that's what x represents, a corner cut out whose dimensions are a square of 0.959 on a side. But let's make sense of this other critical point in the context of the problem. This is a cubic function, so finding 2 extrema was expected. This critical point is a minimum of the cubic function because the derivative goes from decreasing to 0 and then increasing afterwards. But what is 3.041 as a measure of x? If we cut out squares that have a side of anything over 3, and we need to do 2 of them, then that means that we're going to be cutting 6 or more inches out of a 5-inch length, which is impossible. So this critical point here doesn't belong to the context of the real-world situation. It comes out of the math, but doesn't make sense and can be ignored. We have a maximum volume, or we can find the largest box at a cut of 0.959. And if we have an equation to find the volume at any cut length, then we will find the volume at V 0.959. I've done that calculation. It's 15.021 approximately. And since the cut length is measured in inches, then this is a volume in cubic inches and is approximate. Optimization problems are very difficult, not necessarily because of the calculus, but for the fact that you often need to diagram and label and bring together a lot of interrelated concepts and variables in a struggle to find an equation for the thing that you want to optimize in terms of another single variable. If you can find that equation, then you can do the first derivative calculus to it quite readily. Diagram and read carefully the context and think about how you can label the diagram and write equations that relate the variables as a way to get unstuck in these problems.